Good afternoon, everyone. Thank you all from Working Group 3 for joining us today. And I want to give a special thank you to Marianne Piet and Tianzin Hong from the Lawrence Berkeley National Lab, who is going to be providing us with a high-level overview of some of the projects that they have been working on in the realm of load flexibility and building integration. So the goal of this is to provide, again, a high-level overview of some of the projects that they have been working on, with the end goal of identifying any projects that people in Working Group 3 here would like to get a more detailed, more in-depth presentation on. So this is kind of the high-level overview for everyone to just see what's out there, and then we'll reach out after this meeting, maybe tomorrow or on Friday, to put out a survey to the Working Group 3 members to see which topics you would like to have more in-depth presentations on. Again, thank you to Marianne Piet and Tianzin Hong. It's a lot of information and a lot of interesting information, so I want to give them as much time as possible. So Marianne, I'm going to go ahead and hand it off to you. Go ahead and I'll advance the slides as you need me to.
That's great. So thanks, Haley, for getting us organized today. I'm Marianne Piet. I'm the Building Technology and Urban Systems Division Director at Lawrence Berkeley National Lab. And I've also been running something called the Demand Response Research Center, which was funded by the California Energy Commission during the PEER program. And I'll tell you a little about CalFlexHub in a few minutes. But I'm going to go through a portfolio of activities, super high level. The slides have more detail than I will have a chance to comment on. So we wanted to give you that resource. And the last couple of slides will be from Tianzin Hong. And I'll make some closing remarks. I'm going to try to leave at least 10 or 15 minutes at the end for discussion. So I'm going to try to go through these fairly quickly. I'll probably not look at the chat too much while I'm speaking, so I can sort of get through the material, and then we can kind of go through questions in the chat. So go ahead to the next slide. So I've got 5 California activities and 10 DOE kind of national activities. This is a growing area in the United States. California has been working on this topic for quite some time. And I think these projects will give you an idea of the state of research at LBL. There are definitely more. This is not everything, but this is the first cut at what Tianzin and I were able to put together in a pretty short time. Go ahead to the next slide. So I want to start with introducing you to the demand response potential study. This is the cover page from the phase 3 study. You may have heard of shape, shift, shed, and shimmy. Those terms were coined by Peter Alstone, a researcher up at Humboldt State. The idea is that we want to understand the grid services that you can get from buildings. The demand response potential study is an activity. We're actually in phase 4 right now, but phase 3 was the last study that was completed. These studies are oriented towards trying to understand how much demand response potential is available. And this is all sectors. So this is EVs, buildings, industry. And we've been doing this research since about 2016. Go ahead to the next slide. So you're probably all aware of the duck curve. When we started this work, the duck curve wasn't the source of what we were doing. We've been very interested in peak demand and hot summer day demand response. But of course, because of the duck curve, when we think about decarbonization, we want to understand the ability of buildings to help shift electric loads and use more of the cleaner electricity and less of the dirtier electricity that comes around dinner time. So actually, there's a whole bunch of bullets on this one. I'll let you bring them down. Keep going, keep going, keep going. I think that's it. So go ahead back. Sorry. So we're going to talk about shift, and I'll be revisiting the concept of shift. The purpose of the phase 3 report was to look at shift specifically. So in phase 1 and 2, we looked at all of those services: shape, shift, shed, and shimmy. And shape we defined as the ability to respond to dynamic prices. Shed is the traditional hot summer DR, and shift is moving load from one time of day to the other. And then shimmy is the fast acting DR. We're not doing too much in that these days, but that's of course something for ancillary services. So the issue in the demand response potential study was, how big is the shift resource? And we specifically look at HVAC in commercial buildings, HVAC in homes. We've been adding more on electrification of both space heat and water heat. We model EVs. We actually modeled thermal energy storage in the phase 3 report. And we were looking at the capability of different loads, and I'll show you some results in a moment. But the key takeaway is that we need shift. Now, today's demand response programs don't actually pay for shift. And as we think about the needs of the future, we want dynamic pricing and other sorts of things to help the building owners provide shift. And in phase 4, we're looking at all those grid services. So we now have over 300,000 load shapes throughout California, and we will be publishing the clustered data, which has a lot more end-use disaggregation. So we're in phase 4 right now. Phase 4 will be completed in 2022. Go ahead to the next slide. So this is an idea of the annual resource procurement costs in dollars per kilowatt hours per year. So we can get about $200 there. That line is where we put batteries. So we compare flexible load with batteries, and you can see that we can get a fair amount of shift. This is a shift graph. Shift from pool pumps, space cooling, space heating, water heating. Water heating is expensive because of the way we have this. If you're retrofitting a building and adding to water heating, so we have refrigeration here and a variety of loads. And these are very detailed reports, and we could have a whole talk on this sometime. But I just wanted to let you know that these are statewide, and they're a bottom-up research on the ability of loads to provide various grid services.
So Marianne, I've got a question about shift and DR programs, et cetera. Isn't sort of the intent of time of use rates to encourage shift? I mean, there might be some question about whether the time of use rates are providing a large enough signal, but if what you're talking about is repeatable shifting from one time to another, and you know, to some extent not relying on controls, but actually, or maybe controls, but you know, to some extent, some of it's inherent, some of it is based on control, some is just, you know, potentially just even time clocks.
Right. Yes. So
is there a big need that you see that time of use is just not satisfying the need for shift in our load profile?
That's right. We see about a 2 to 3% change in the electric load shapes because most of the response is manual. We are looking at automating TOU, and we want those prices in the midday to be like lower. The TOU is high, but that midday price is not lower. If we had that differential, it would cause more shift. So we want to move towards even something like real-time pricing or more time differentiation than TOU is offering now. Go ahead. Okay,
so there's a big issue. It sounds like because you know, if you're a technologist, you look at technology, but it seems like the economics or the rates schedule is also equally important. Absolutely. For this.
Absolutely, yep. Yeah. There's no incentive for shifting yet. We did have the excess supply pilot where PG&E was paying people to take, and we don't want take without shift. So it's a long. Let me get to the end, and we can and I will be talking about some of that as we go. Go ahead to the next slide. So I'm gonna this is a CEC Epic project called HP Flex, Heat Pump Flex. This project is around the ability to create an open source control system that optimizes energy use for building owners. It's oriented towards small commercial, and we're looking at the kinds of technologies that we need in buildings to provide that kind of shift. And this is using model predictive control. It is oriented towards using heat pumps for heating and cooling. So a space heating and a space cooling automation platform that has the ability to take grid signals and provide some of that shift. So we'll actually be testing in real buildings the ability, this independent of the price signal, can these buildings provide shift with this kind of technology? And we may want, you'll see in there, the optimal control of storage for enhanced load flexibility. We know that if we have thermal energy storage for heating or cooling, we could shift much more of the HVAC load, which is one of the more important loads for buildings. Go ahead to the next slide. That previous project is utilizing some of the technology that came out of this project. This is called the Solar Plus project, and this is a microgrid up in Humboldt. This particular one is at a Indian casino. You may be, there's a famous one called the Blue Lake Rancheria. Well, this one is the convenience store right next to the Blue Lake Rancheria. And our original goal was to use the cold beer as our thermal storage, but we do have Tesla batteries. So we actually were looking at how many kilowatt hours we could get from beer. We don't want to change the temperature of milk, but we were looking at whether the cases could actually be a type of thermal storage. And I don't think we ended up doing too much of that. There's always an issue on the size of the refrigeration system and whether or not they have VFDs. But the other idea was also to use model predictive control and to field test this at a gas station and to test the ability of the control system to respond to dynamic pricing. And as we mentioned earlier, in the research projects, we send proxy signals. We're not sending the actual signals. We actually need a lot of work still on getting the prices right. And I'll talk a little about that in some of the other projects, as I mentioned. But we're very interested in the underlying capability to control and create dynamic electric loads that include buildings and storage, and it may or may not have photovoltaics. Go ahead to the next slide. Okay, so price-based grid coordination. The state of California is working with stakeholders across the state to develop something called load management standards. And we're working on the architecture of how you send prices to devices. Now, the word OpenADR doesn't show up here, but we've been working on OpenADR. OpenADR will have its 20-year anniversary next year. We started on OpenADR in 2002, and we've been working on it for quite some time. So we want to create, one of the issues with prices to devices is you need a common language to send those price signals to the building. And these different, the picture here is to show whether or not it's coming from a third-party aggregator or coming to some building entity or some DER. And we're working on different ways that we can send prices to devices. That's still the cheapest thing to do. Now, I think it's important to recognize that when we use prices to devices, we get so much response from price response. We get, for example, on a spring day where the duck is deep, you want low prices in the middle of the day and you want high prices around dinner time. That's the day with the biggest difference between the belly of the duck and the head of the duck. The summer's flatter, but the summer has extreme events and hot summer days. So when we have extreme events, we may be able to send an emergency call on top of a dynamic price. So it's important to think about that we get so much demand response just from prices. Now, if you sent extreme prices, you're going to have things like Texas, where people, are people going to be exposed to the wholesale market prices or not? And what is the way to actually formulate prices that we actually use scarcity pricing? So as was mentioned and will continue to be, getting the prices right and getting prices that reflect system conditions and understanding how price response a building can be is a very important topic, and there's still work needed on that. But we're working a lot with the state of California, and CalFlexHub will be doing this, on testing the ability of smart thermostats, heat pumps, water heaters to actually receive common prices and create that automation that's going to be required through SB 49, through load management standards. And the utilities are going to be required to publish their tariffs in a standard format that the CEC's been promoting. So there's a lot of work to make sure that the utilities are getting those prices into the price server system, and they're going to be simple TOU, but over time, critical peak pricing as well as real-time pricing. Go ahead to the next slide. Now, CalFlexHub. So CalFlexHub is a large program. It's a 4-year, $16 million activity with the interest in creating a better understanding of how buildings can provide flexible load. Two key things here is what are the technologies? So we have 12 projects, 6 more research oriented and 6 more field demonstration oriented. And those projects include all sectors. So residential, small commercial, large commercial, multifamily, disadvantaged communities, space heating and space cooling, thermal storage, water heating, EVs. So we're going to be looking at a variety of technologies, and we're going to be testing that capability of getting standard signals to devices and making sure they can respond, plus using the watt time signal, so greenhouse gas signal. And how different is the utility bill if you're responding to a price or a GHG signal? So we'll be doing a variety of work on helping to test the ability of using this common format to get the signals out. Go ahead to the next slide. So the way CalFlexHub is oriented is that we have a set of initial 12 technology projects, and every year you'll see this annual review cycle at the top. Every year we'll be looking at how those technologies are performing and trying to move them into the field and understanding, are we investing in the most important technologies, and what are the usability issues? What are the business model challenges? How do we develop the right metrics? And we'll be using some of that demand response potential study framework, and E3 is involved. So we'll be looking at a variety of metrics associated with the performance of the technologies. So that's basically a quick overview of CalFlexHub. We're working on valuation methodologies. We're working on technology performance. We're working on price response. And we're working on business models and deployment, partnering with the utilities and a variety of technology vendors around the state and around the country. Go ahead to the next slide. So I want to remind you, this says draft March 29, 2021. That's actually not true anymore. That the U.S. Department of Energy has launched finished the National Roadmap for Grid Interactive Efficient Buildings. You can find it at GEBroadmap.lbl.gov. Go ahead to the next slide. So the roadmap is the first attempt to try to look at the potential for grid interactive efficient buildings. So the word GEB is acknowledging that energy efficiency is good for the grid also, because if you can lower the energy use for everybody, the grid doesn't have to be as big. Now, energy efficiency in the middle of the day can make the duck curve worse. So there is a time value of energy efficiency, just like there's a time value of electric load. As we finished up the roadmap, we were also saw a new administration that was very interested in carbon emissions. And so the GEB roadmap was written around what is the agenda and who needs to do what to advance the concept of grid interactive efficient buildings. So on the 4th bullet there, DOE has established a goal of tripling the energy efficiency and the demand flexibility in the residential and commercial sector by 2030 relative to 2020. So the roadmap has these 4 pillars of activity. Through R&D is the first pillar, enhancing and communicating the value proposition of GEBs, empowering users and operators of developing new tools and training, and then partnering with federal, state, and local government. So the CEC is a great partner. The way I think about this is, if you're working with a city, if you're working with a state, GSA or DOD, we want the state's buildings, we want DMVs, we want DGS, we want the state buildings to be early adopters of these technologies, and we want to understand, just like we have in 40 years of energy efficiency, what the retrofits look like, what the costs and benefits were, what are the barriers to the retrofits. And so when we do an energy efficiency retrofit, we really want to think about the electric loads, and a lot of that has to do with controls. So when we're putting in lighting, making sure we're putting in the controls. If we're retrofitting the HVAC, now the dynamic facade may or may not be part of the equation, but generally when you put in better windows, better insulation, and a cool roof, you can downsize the cooling system, maybe downsize the heating system. So if we're doing those electrification retrofits for heat pumps, we want to do the envelope first before putting in that heat pump. And the GEB roadmap sort of goes through what are the recommendations for the different stakeholder communities to advance this effort throughout the United States. Go ahead to the next slide. Now, this project is a really exciting one. I spent a lot of time on this one myself. I'm the PI on it. And this is about developing the metrics to characterize what load flexibility is available in commercial buildings. We are developing a set of metrics. One of the primary metrics is on that bottom figure, the demand decrease intensity, like the watts per square foot. So in the United States, the average office uses about 6 watts a square foot. You'll see here about 0.1 to 0.5 watts a square foot from these different shedding techniques. The most common thing we do is change the zone temperature. So we call it global temperature adjustment. And often if you're running the building at 70 and you move up to 74, there's some mass in the building that allows you to be comfortable for so much time. And depending on how much mass there is and what the VAV boxes do, you can get a watt a square foot sometime. So we look at what are the factors that influence how much electric load can you change in a building. We're focusing in on 4-hour events. So these are tending to be sort of historic DR data. So we want to look at EnergyPlus simulations. We look at testing and FlexLab and real facilities, and we look at field data. So we have field data from California demand response, and we have a big box retail with many sites around the country. So we're trying to understand, can I get half a watt a square foot? Can I get 0.3 watts a square foot? And what drives that? What are the things that influence the ability of the building to provide some kind of a shed metric? So we look at the magnitude and the variation. We're focusing on summer, but we will be doing some winter analysis. And we look a lot at the role of the envelope and how windows and the envelope influence it, whether the surface area to volume ratio, so how a large building performs compared to a small building. And maybe larger buildings have more efficient HVAC. So the watts per square foot may be different for HVAC. So a variety of factors to try to characterize what we say about what those metrics are and kind of benchmark the demand flexibility metrics. Go ahead to the next one.
Well, Marian, would now be a good time to take a second and look at some of the questions we've gotten in the chat?
Sure. Sure.
So the first question was from a bit earlier. I think it was from maybe the second project you presented on, but Ted asks, have you considered carbon intensity on the grid as the trigger for shift technologies rather than relying on cost embedded in historically lagging rate design?
Yeah, so we are testing the watt time signal, which is basically that. It's a real-time grid carbon intensity signal, and both the state of California as well as our research, we are looking at real-time carbon. Now that you can get that in California, but that's not available throughout the United States. But yes, for California, we can control on a carbon signal. But how different is that carbon signal from the retail rate? Mm-hmm. So in general, the more those are coupled, the more the owner's going to be incentivized to follow that watt time signal. Is he willing to pay a little more to be cleaner operational energy? Maybe.
Okay. The next question is from John Bade. This was, I think, maybe 1 or 2 projects ago, but is the federal goal to individually triple both energy efficiency and demand flexibility, or do they mean to reduce peak demand by 3 times by some combination of the 2 techniques?
Yeah, that's a really good question. And energy efficiency and demand response are sort of coupled. I think it might be my next project where I'm talking about that. But the one, slide 4. So so basically, I think, how should I answer that? I would say that the grid interactive nature of building loads is newer than energy efficiency. So we know how to get more energy efficiency. We know less about how to get more dynamic load. And hot summer peak is only part of the challenge. And so those goals were actually written around hot summer peak because that's easier to quantify than the flexible load. So I'll leave it at that.
Great.
Another question?
No, but Ted's following up from that first question on real-time pricing for carbon. And he says that CalBEM data will cover the rest of the US. Yes, alignment of carbon and cost needs to happen in rate design. Following up with watt time does have real-time data sets for the rest of the US as well.
Great. Yeah, so we're definitely looking at that, and again, the more we can align rates with carbon, the better uptake we'll have.
And we're all caught up on chat questions. Thanks.
Thank you. So let's see, on slide 3 here, these are now, as I mentioned, these are the DOE projects that we've moved into. And this project is called FlexAssist. And it's developing using discrete choice analysis, a model to characterize how a building operator may make decisions when they're responding to a demand response event. So it's a probabilistic Bayesian decision network, and it integrates a risk-benefit trade-off with the operator preferences to select a set of candidate DR responses. So it might be a change in lighting, it might be a change in temperatures, it might be elevators or plug loads, and all of those things may have the ability to respond to some sort of signal. So this project has involved a huge amount of surveys across the United States, and we're in the process of collecting information from actual operators about what kind of choice would they make between sort of comfort and utility bill savings. And of course, a operator may really be concerned about doing any of that. So it's an interesting project that's still in the process of developing the tool. Go ahead to the next one. Okay, so this is about at the utility system level, what is the relationship between energy efficiency and demand response? And we wanted to acknowledge the fact that it's a complex interaction. That's the first thing I'm going to say. We want to be able to maximize resource co-benefits. And in California, sometimes we call it integrated DSM or IDSM. Integrated DSM may include energy efficiency and DR. It also may include energy efficiency and DR plus DERs, like a PV and a storage electric battery. And that's one of the things I haven't said is that the GEB Roadmap focused on building loads, but how we think about the electric battery and the photovoltaics and the behind the meter DERs is a huge challenge that's going to continue to influence the way we think about energy efficiency. So the bottom line is, for 4 decades, our concept around energy efficiency was stable, but I think it's changing because as the grid changes, the value of DSM measures change significantly. So in this project, we are actually looking at, from a building perspective, a change in the demand flexibility, a change in the participation, and then what does the utility system need, and what is the change in utility response? So it's a complex issue on how these things. So there are times where energy efficiency and demand response may be synergistic, and times where they compete. For example, if you put in a good envelope, you may decrease the demand response because the cooling load's less. Now that's a good thing, but it's just important to recognize what your goals are. And a lot of people will say, well, if I put in energy efficiency, it'll change the DR, and it will. In general, you want to do the energy efficiency first, but it's not so straightforward. And it really depends on some of the challenges at the grid level when the utility regulators and the utilities are trying to figure out what are the goals for their DSM programs. So energy efficiency controls measures tend to complement DR, but we're just acknowledging that there's some interesting tensions between energy efficiency and DR, and this project is exploring how when they compete and when they're synergistic. Go ahead to the next slide. Now, I'm super excited about this project. I've mentioned model predictive control. So this project, we're looking at occupant responsive model predictive control. So we're doing a lot of work on measuring when people are in a room or a building. And you see it says at the room, at the building, and the campus level. And so the idea of model predictive control is that we actually use energy use of the building as part of the sequence of operations. And today, the building runs, you do set point optimization. You're actually not minimizing energy use. The controls are basically providing comfort and schedules. But we really need to move to a time where we can send sort of grid signal, and the building control system looks at the forecast of weather, the forecast of occupancy, the forecast of grid prices, and decides on set points to optimize the ability of the building to respond. So we have a building at Lawrence Berkeley National Lab where we have several RTUs, and we're doing a very, very detailed MPC activity. You're probably aware there's something called white box models, which are more physics-based models, and black box models, which are more data-driven. And we call this a gray box model. It's using some of the physics and some of the data to create the models in a Modelica framework. And we're using these models to do set point optimization. We are listening to the watt time signals in this activity. And it says, so we're doing a building at LBL and then a campus. It says using ice storage. We're actually using, it's actually chill water, not ice. So we have it out at UC Merced. They have a large chill water tank, and they have 2 megawatts of photovoltaics. And we're actually changing the time that they charge the TES. So historically, TES is charged at night, but we're actually, they have their own duck curve shape. So at UC Merced, they're not able to use all of their own megawatts, and they sell some back, but instead of selling back those extra megawatts, we're actually using them to charge the TES. So we're creating a carbon minimized operating system using MPC, and we're reducing the utility bill. So we're actually closely watching the peak demand charges, and we're using a variety of these technologies to control the UC Merced TES and integrate it with their own PV. So that's it, and we're testing their ability to listen to the watt time signal. I see a question, I think.
So this question's from John. He's saying that a lot of the discussion seems to be about non-residential buildings, but aren't many non-residential buildings closing and their loads dropping during early evening hours when the duck curve is most problematic. Does this result in placing more focus on residential applications, which are coincident with net grid loads?
Yeah, that's a really good comment. The next slide, I'll get to in a moment. You don't need to change it yet, but the next slide, we certainly want to do both residential and commercial buildings, and you are right. The load is more influenced by homes because people are starting to go home. They're still at Whole Foods, they're still at Target, and they're still at the UC Merced campus. Office buildings do typically peak earlier in the day, but there are a lot of commercial buildings, hotels, restaurants that are still peaking later in the day as well. So we still certainly have some building types, but you're right, the residential load becomes more important, and I will make a comment about that in a moment. And a lot of the techniques that we're talking about, they're relevant to residential and commercial, but yes, it's a good point. Go ahead to the next slide. Okay, so hybrid HVAC with thermal storage research and demonstration. So here we are looking at thermal batteries and various types of phase change materials, and how do we integrate them with commercial and residential? We've been working on developing Modelica models, developing open source hybrid systems, doing a field trial in residential, but with significant heating and cooling, and building and testing a commercial prototype. Now, of course, it's more expensive to install TES in homes. There's a lot of soft costs, and that's why you see chill water tanks at our campuses where we have district energy types of systems. You may see storage at a hospital, or you're probably aware of the CalMac ice energy systems and such, but you don't see it much in homes, and it's expensive. So we really want to be able to make these things more plug and play and modular, and be able to deploy storage, because storage is one of the most important things to move that load when people get home from work and they're turning their air conditioners on. If there was a cool storage tank that they could draw on, we could really reduce the duck curve and charge that tank in the middle of the day when we have more clean electricity. So this is an ongoing area. The U.S. Department of Energy is going to be launching a thermal energy storage consortium. And it's a important topic because the electric battery is actually often more energy intensive. We can be more energy efficient with TES than electric storage. So electric storage, obviously, we store it in DC and we have to get it back out in AC and go through an inverter. With TES, hopefully we can match the size of the system with some of the loads and have round trip higher energy efficiency. So I see a couple more comments in the chat.
Yeah, these are follow-ups from the previous conversation. Kelly Cunningham asks, are you exchanging information with Ellen Franconi at PNNL on the TES project? There is some ASHRAE work happening to reward chilled water TES. There's a working group on the topic that may be interested in comparing your results to their assumptions.
Yeah, so Spencer Dutton is the lead for this. I think Ellen might even be on. I thought I saw her. But yeah, so we should. But that's a good comment.
And then a comment from John Bade. The downside of daytime charging is that the chillers have to be sized to support both daytime cooling and TES charging. Yep. The big selling point for nighttime charging, at least in other parts of the country, is that the capital cost of the system can be the same or less than a conventional system.
Absolutely. You know, I mean, they run more efficient at night, but if you're using carbon, so looking at the life cycle costs, there's a lot of work needed on that, and we haven't started that, but that's an excellent point.
If any commenter wants to, voice up and read their own comment, please feel free. But I'll continue to be narrator otherwise. Garth Torvestad has another comment here. You said earlier that one of the studies was focused on load flexibility from the perspective of summer peaks, but also starting to look at winter peaks. Do you anticipate that these winter peaks and the need for load flexibility will eventually eclipse summer as we electrify space and water heating? How are winter demand response strategies different given much lower PV generation in winter? Does this refocus load flexibility on non-res buildings, since NR heating peaks occur on winter mornings?
Yeah, so it is possible that California would become winter peaking. I've seen those numbers, and if we think about efficient electrification, we could become winter peaking. And yes, but remember, many commercial buildings don't use much heat. The bigger they are, they have a lot of internal gains. Of course, they have less internal gains because LEDs are so efficient. And your facade really matters, just as it does with cooling. But having a good windows and a good R value and a good insulation and infiltration. So that's a good point. But we still have the problem of the morning peak. The morning peak, which is residential driven, is of significant concern. And it's possible that you could, again, kind of preheat having some sort of storage or even preheat mass. People don't like to be real hot when they wake up in the morning. And there's been some work in Canada. They have electric resistance heat, and they've been looking at the ability to respond to open ADR signals. So that's a good comment. So I have one more slide before I pass it over to Tianzin for a couple from him. So I want to make sure we have time at the end. So this is the last one from me, and Tianzin's going to do the next three. This is a framework to characterize demand flexibility of buildings with something called a hardware in the loop approach. And this is mostly using FlexLab, which is a set of side-by-side test beds with a real HVAC system. And we're creating a variety of Modelica models where we're testing part of the system is real and part of the system is virtual in a model. And today we had a long discussion with DOE about phase change materials in the ceiling panels and potential thermal storage batteries. And we're developing models that characterize load flexibility, both at small buildings and medium buildings, mostly offices. And I think I'll stop there and let Tianzin do the next three.
Thanks, Marianne. Next slide. So I have 3 activities to talk about. These are more related to modeling and simulation tools to support, demand flexibility simulation. So the first activity here is under the sensor data integration project. So basically, right, when we try to model the demand flexibility, one key element is to understand how we represent the flexible resources and loads in buildings. An example would be water heating loads, laundry loads, EV charging loads. So those have, flexibility. You don't have to, right, fix when the loads occur. So, there's a need to represent those loads, that when they can occur and, for how long. And so we have been review literatures and try to understand, whether there's any existing tools. On the right, you see this ecosystem. And so basically there's still a gap how to represent the flexible loads and resources in sort of a standard way that facilitates the modeling, for between different tools. So this activity basically try to develop this ontology to represent these flexible loads, and that would work with this existing ecosystem, to facilitate a gig, on demand flexibility modeling. So let's see. One other thing is that TV try to do is also, earlier Marian mentioned, right, it's a metrics to represent demand flexibility. So the ontology will try to also cover, to represent these KPIs of those, metrics, and also link to what kind of sensor and meter data are needed to calculate those KPIs. And those would link to, the building's operational, data. Next slide. So these activities, so this is part of the EnergyPlus project. So, collaborating with other lab and other, companies. And so EnergyPlus, right, for the last 20 years, one of the feature development is to support demand response modeling. So I think if some of you use the feature, so basically supports the, demand flexibility from, dimming lights, switching lights off, play with the plug-in equipment, and adjust the thermostat, as Marian earlier mentioned. There's also you can control, increase or reduce the, outdoor ventilation air, and that is, something now, allowed by standard 62. So the recent activity is to think about the HVAC equipment with more VFDs technology, right, implemented as part of the, HVAC, like fans, compressors. And so this activity basically is to allow those kind of speed and, control using an EMS actuator. And the logic can be written from external, tools, external code, right? And through this Python EMS now provides a lot of, flexibility for the control logic to work, directly controls the speed of the fan, compressors, and other HVAC, equipment. So you can model those kind of needs using the, some of the new features are coming out of the EnergyPlus tools. Next. So this is the last project in the DOE's portfolio. So with gigs, right, it's probably a dozen projects, right, looking at the different aspects of the, the gig. And so we have tried to consolidate, all different OpenStudio measures in sort of an OpenStudio extension gym. And the idea is just to standardize, these are measures, but also put in more QA, QC quality controls and include a measure to report the results. Otherwise everybody sort of like have their own code to reporting the different metrics. So this is trying to, massage and integrate those things, and using some of the existing measures already developed from different projects, also part of the OpenStudio's building component library. So most of those already developed measures basically use lots of like hardwire assumptions inputs, in the code, which is very difficult to be directly used for other purposes. So basically this activity is trying to make the measures more generic, more standardized, put in the quality control, as well as adding a report measure. So on the right side, you see there's about 10 technologies, we are working on as part of this fiscal year, and these are very traditional things like preheating, pre-cooling, thermostat adjustments, lighting load adjustments, electric battery charging, and so in the future they will expand, more measures into this OpenStudio, gym to facilitate, more modeling. I think this is the last one. I think I'll turn to Marianne for the summary.
Yeah, so I just wanted to make a couple of quick comments, and then we can open it up to more general discussion. But the picture here is showing that we're moving from static energy efficiency to dynamic energy management. It's actually a little bit blurry. I apologize for that. So the building, we have growing need to understand these numerous dimensions of building controls. We care about, security, worker productivity, worker health, lighting, HVAC, air quality, and the building is in many cases becoming parts of microgrids, part of a campus of buildings. We have EV charging, and EV charging is an interesting one because it's not a building service, it's a transportation service. So we have a lot of challenges when we start thinking about the different end-use services that are provided by electricity and how we consider the EV charging in an electric load shape. It's a real issue for a lot of our accounting and a lot of our look at what we historically have done in building end uses. So we now have these transportation end uses that are going to be growing. The EV charger may be on the whole building meter, it may be a separate meter. It may be with a home or a multifamily building, a campus or an office building, or a district scale system. So we have a lot of complexity. And bottom line is we are all interested in understanding affordable decarbonization. So I appreciate the opportunity to talk with this group because using carbon as a metric is, of course, of growing interest. And there's a lot of complexity there as well, because there's today's grid and tomorrow's grid. And we now have the time differentiation of electric load and how that interacts with the grid. One of the key things as we think about buildings is how we retrofit a bundle of measures. Do we just look at energy efficiency, or do we add demand flexibility metrics and DERs? So we want to be able to understand packaged retrofits for existing buildings and create bundles that are kind of cookie cutter for different building types. You can imagine a city block in Oakland that all has the same vintage homes. There's a typical retrofit package that might be best. And maybe that retrofit package comes with or without a battery or a PV. So we're really interested in scaling our retrofits. And of course, thinking about underserved communities. I didn't mention on the load management signal, but we will be using FM signals in addition to open ADR and watt time signals that may be over the internet. Sending FM signals does not require somebody to have Wi-Fi. So there is definitely a lot of interest in making sure we can get signals to equipment and making sure that we're aware of the various implications of the decarbonization agenda for different communities around California. So I'll stop there and we can open it up to, I see a few more questions.
Let's see here. So first question on our list is from Neil. I think that's Neil Cruz. EnergyPlus EMS is almost always lagged by a time step. Won't that be an issue for responding to signals without using very short time steps and a longer simulation time?
Maybe I can comment on that. I think, Neil, yeah, that's correct. So I think for most of the demand flexibility, like Marianne already illustrated, those are probably simulated at a few minutes, time step, obviously. So most of the time this will be fine. But if you're looking at very fast, dynamic, like a shimmy, you're probably right, and it needs to use some other tools like the Modelica based tools.
And everyone feel free to jump in if you have follow-ups on your questions. Next question, I believe this is John McHugh. and I'm not sure if I'm interpreting this correctly, so John, please jump in if needed, but demand response requirements in code require that it be temperature based so that the system is not causing people to suffer excessively. For example, closed loop control. Open loop reduction in fan speed creates potential problems of customer retention and temperature. Customer retention is temperature excursion. Oh gosh, John, do you want to jump in here? I'm not sure I'm getting the point across well.
Yeah, so that word should be if. So creates potential problem of customer retention if temperature excursion is excessive. I'm trying to understand the eventual link between this sample control with code outcome. There have been manufacturers, I think it was back in 2013 or something like that, where some of the manufacturers of I think it was variable refrigerant flow systems wanted to have an open loop control and just wanted to adjust the speed of their control. And, this kind of goes back to, demand cycling, which, there's a certain fraction of the customer base that finds that obnoxious in terms of temperatures being too high. And so, the code saying this is a minimum, it's supposedly an efficiency standard, so we're not excessively impacting human comfort while we're trying to manage demand. And so just sort of wondering, how might this type of control that sounds like it's open loop be applied to code if what we're trying to do is balance between comfort and demand response? Thanks.
Yeah, I have a couple thoughts. I do think that the global temperature adjustment, which is mostly for commercial, I think it was a 4-degree reset. The controls had to be able to do that. And let me make a quick comment about that. Global temperature adjustment is if you push a button, all the zones go 4. When we actually went out to retrofit some control systems, that was easy to do, and other ones you actually had to reprogram every zone. It's a huge amount of work in some buildings to retrofit that. But in new construction, that was the idea, was that you would have from one point the ability to reset the zone temperature. Resetting the zone temperature means that the supplier reset and the zone temperature, all the resets, the chill water reset, all those happen downstream, and you're controlling at the zone. So you're right. If you just set it by 4 degrees, you're not going to get above 80. And if it's a really hot day, you may not get any demand response.
Yeah, and I'm familiar with GTA
Yeah.
and that's what's implemented in the code since 2008.
Right. So I think the VRF is an interesting problem. I also think for homes and even for commercial, we don't have to cool every zone. So certainly for homes, when you have central air, if we could zone better, we might say, I'm going to keep these rooms cool and I'm going to let those other ones heat up. We probably don't do enough of that. And that may be an extreme event response. And I know, a lot of us don't have air conditioners here in Oakland. And so I have one portable. So there's a lot. So the answer is, I think it's a really good point, and we need to better understand how these systems perform in the field and what the opportunities are for the different strategies for closed loop and open loop systems. So that's my inclination. Is it's a really good question for some field work. If you think otherwise, let me know.
Right, and why I asked the question was Tianjian, described the just an open loop control of just adjusting the fan speed for, I'm assuming, which is a multi-zone system. Is that, did I miss that? I mean, that's why my question arose. Was it appeared that as part of your simulation process, you're proposing to adjust the fan speed and not use GTA? So I'm just trying to understand, what does that mean? And what's the thought in terms of that trade-off between comfort and DR? But I hear you, Marianne, that there may be some opportunities for multi-zone systems where you identify areas that are you could control even further, right? Non whatever the word is, critical, right. or non-populated zones or whatever.
Yeah.
Yeah. So John, I think two things to add to that. One is the comfort. So the ASHRAE, right, Global Thermal Comfort Database basically shows the cooling, temperature has a range, And so that's some flexibility if needed that people can tap into. And obviously, right, I think Marian earlier presented a project, FlexAssist, that provides a toolkit for building operators to make decisions. Right, there's different ways you can share, you can move, loads, but it comes with benefit and cost. So I think at the end, of course, right, those needs to be considered. Yeah.
Yeah, and I'll just share with you, we've had the 4 degrees since 2008, but when I've brought the same sort of proposal forward to ASHRAE Standard 189, we got a lot of pushback from members that more than 3 degrees they felt was starting to impact on human productivity. So I just share that with you.
So we've got two more.
But yeah, we're living with 4 degrees. I mean, we have for a long time.
Yeah, it's not that much.
As we roll into our last 2 minutes, we got 2 more questions. The first is from Alex Chase. Great presentation and info. Thank you. From your perspective, what are the biggest data gaps related to your efforts? What would be the most helpful issues for the building energy modeling community to work on at this point?
Yeah, so it's always field data, understanding how these technologies actually perform in the field, and that I think is the biggest gap. Tianzin, do you have other thoughts?
Yeah, more the second part of the question. I think the simulation community, right here, we should think about how to expand existing tool like a building information modeling, building energy modeling, to come up with those ontology to represent the flexible loads, and come up with more, a standardized workflow that work with across tools, across applications, and I'm sure those can be sort of benefit community code development effort.
And then I think we can sneak our last question here from Neil Cruz. California is looking at adding compliance credit for demand response technologies and controls. Right now, the only signal we can use as a proxy for demand is TDV. It's hard to imagine adding a separate signal for these simulations. Do you think this is a reasonable approach?
Yeah, I think it is. The only thing I'll say is in some of our demand flexibility metrics work, we're trying to do a GTA during the 5 hottest hours of the year, or some testing. If you had a way to say, when I do GTA on these days, I get this many watts per square foot, that would help us benchmark the simulations. And Tianzin, I don't know if you've thought about that, but I know you've looked at our data also.
Yeah, I think definitely. So that's earlier, I think Mary, you mentioned, right, we use a wartime signal, right? Those are more on the building operation, side. And I think, Neil, it's also proposals, right, to enable EnergyPlus, right, to consider those kind of, signals to control how the, different energy systems would operate.
So we're at the bottom of our time here. I first want to thank you guys so much, Marianne and Tianzin especially, for being our contributors from LBNL today. Haley, Neil, did you have anything else you wanted to add before I close out here?
No, I would just say thank you for the slides. They're available to everyone. There are a lot of really good questions out there, and there's a lot of information on these slides that obviously Marianne didn't have enough time to go over. So again, the goal here is to identify some of the projects that we'd like to get some more information on, and maybe follow up with additional presentations, more in-depth presentations on. I'll work with Elise to reach out to the Working Group 3 members and figure out the best way to get that information, which projects we want to focus on.